Swayam Prabha. Digital India. Educated India.
We have been looking at net energy analysis and life cycle analysis. We continue with that with some examples. Before we do that, let me just again tell you about the criteria that we talked of. We talked about the energy return on investment, EROI. We also looked at the energy payback period, which is energy payback time, EPBT, and then the net energy ratio, similar to the energy return on investment, net energy ratio, NER. Remember, in the NER we were not using the renewable energy sources in this. In addition to this, there are two other similar indicators which we will use, which is also used in literature. One is called the cumulative energy demand, and this is often done even for products. That means, we take, let us say we are making steel or we are making cement, we take the total amount of energy which is required in the over the lifetime, energy input over the life, and divide that by n, which is the number of years of life, and the output that we are producing. So, if you are looking at a production, M product annual. So, you take the cumulative energy over the lifetime, that is the energy input, divide that by the number of years into the annual production. So, this is called the cumulative energy demand, and we can compare the CED for different process routes and see overall whether or not our option is better than the baseline. Similarly, we have what is known as a carbon emission footprint, and this will be the total carbon dioxide or carbon emission, whichever way you would like to do that, over the lifetime, emission over the life, divided by N into M product annual, right. And so, what I will now show you is our examples of net energy analysis that we have done in the Indian context. These are all based on different student projects. Some of them are at the master's level, some of them are at the PhD level. So, we will take, this will give you an idea of how this analysis can be used for different kinds of context. And at the end, we will talk about what are the advantages and disadvantages of using net energy and life cycle analysis, and how do they compare with the conventional economic analysis. So, let us start with an example. This is an example of different, many researchers believe that the future will be with hydrogen, and hydrogen is a secondary fuel, secondary energy source. The key thing in terms of using hydrogen in a transport sector would be how do we store the hydrogen. So, there are what we looked at here is the different kinds of, we can have, like you have the CNG, compressed natural gas, we can also have compressed hydrogen storage, and these will be at high pressures, and then we can also look at liquefying the hydrogen so that the volume gets reduced, and then you have a cryogenic tank. And we could also have solid state storage, metal hydride, and there are a number of people who are working on different kinds of metal hydride. So we can look at magnesium hydride and FETI hydride, and in this we can, for a certain amount of distance which we are riding, what is the amount of energy which is being consumed, and the direct energy required for travel, energy required to produce and store the hydrogen, energy required to produce and store produce the tank, and so we get the total energy required for the tank. And you can see that some methods of storage have relatively less energy that is required. So for instance, magnesium hydride seems to be better than FETI hydride, and if one looks at it, in the case of the production and storage, in this case you will find that for cryogenics there is a significant amount of energy required for this storage. The add-on materials, so when we look at the total, it turns out that the FETI hydride is lower than the magnesium hydride, even though the energy reduced to produce the tank is lower. And so that depends on the performance, and we can use, for an equivalent amount of performance, we can compare. And right now, as it looks like, the compressed hydrogen tank seems to be the from an energy point of view the best option. Of course, there are the issues in terms of safety, and solid state storage account better for the safety. In the case of solar thermal power, we've done an energy analysis for the both parabolic trough collectors and Fresnel reflectors. In all of this, first what we did is we defined, for a particular amount of output which we require, a 50 megawatt plant with a particular amount of output. We defined the different characteristics for a particular location, and then calculated the amount of steam, and then the solar field requirement and the field area. And having got that, we then calculated the dimensions of the modules, module length, module width, number of modules, the oil volume, the piping volume, receiver volume, the vessel dimensions, and then we have an embodied energy factor for each of these materials. So you have the solar field, the steel and the glass and the mirrors, and then you have the receiver, mirror weight, structure weight, the energy used in this, and then we got the energy payback period and the energy return on investment. And it turns out that for the parabolic trough collectors, the energy payback period turns out to be higher than that for photovoltaics, but even then it's of the order of about a little less than 4 years, which means that it could be viable, because the solar parabolic trough collectors last for 25-30 years. And so with the result that even though the economics today of solar thermal doesn't seem to be it's a little costlier than the conventional, from an energy point of view, you recover your energy investment in less than 4 years, and then the remaining part is basically the advantage, and you are going to get the NER is going to be greater than 1. In the case of buildings, one can look at different types of in a building. There is a significant amount of energy which is used in the operations. And one can look at different kinds of materials. If we are using more insulation, we are using phase change materials, the initial embodied energy of the building can be slightly higher, but that can reduce the operating energy. And so if you look at a sustainable building, you will find that the embodied energy component as compared to the baseline share of the embodied energy is slightly higher, but the overall energy gets reduced. And this is another area where there is a very significant scope for improvement. We can compare different kinds of materials, we can look at what is the embodied and the operating energy, and then calculate this, because buildings overall are extremely important. 30 to 40% of the total energy use is associated with buildings, and if we can design the buildings so that the life cycle energy use is drastically lower, then we can use renewables to supply that, and we can have a sustainable solution which is distributed. So now we'd like to show you some results that we have done for a situation where we are comparing distributed PV battery systems, and we want to look at different kinds of batteries which are there, and we've done an analysis, cradle to gate kind of analysis of the different types of batteries, and try to see what it means in terms of embodied energy. So if you look at the batteries, I just like to show you some of the steps involved and how one goes about this analysis. For more details, you can see the paper which has been written by Jani on this project. So we can look at, for a particular amount of we were looking at a particular amount of electricity which is being generated, and if we look at by weight, if you are looking at a 1 kg of a lead acid battery cell, the manufacturing, the battery assembly has anode, cathode, electrolyte, and you can see the amount of different materials which are there. For each of these, again, in the case of lead, is a question of how much is actually purchased and extracted and how much is coming from recycled, and that share, that fraction affects the overall calculation. Similarly for aluminum and recycled aluminum. So these factors can be varied, and based on this the numbers will change, and you can see all the different components, separator, tubular mass, connectors, and the assembly of the battery, all of that is put into it. When we look at the overall cell, we are the PV battery system, we are looking at the manufacture and transport of the PV array, production and transport of the frame and the array support of the solar charge controller, the battery, the inverter, and then based on this we get, for a particular output, we can make this calculation, and this gives us all the different steps in the life cycle analysis so that we can get the total amount of energy that we are getting in this system. So if you see this, this is the this is another picture schematic of this, which talks to which tells us silicon production, PV cell manufacturing, fabrication of the modules and frames, the materials which are there in it, and then we have the batteries, and then the installation phase, operating phase, and then material recycling and the waste disposal. In this case, we just concentrated on this, and we have not added the waste disposal phase. So this is for the this is the cradle to gate. If we wanted to do the cradle to grave, we would have also needed to take the decommissioning and recycling and the transportation of this. So in each of this, there is materials, there is embodied energy in the materials, there is the electricity and the energy use which is there. And just to give you an idea, when we talk about lead or aluminum, there are variety of different sources which give the amount of energy per kg. So you can see here the from this is the what is known as virgin lead. That means if you are just directly getting it from the ore, it varies from 22 to 39 different. We've used this as 39.1, These are for other contexts, Europe and others. We have taken the location of the mine, the kind of ore that we have, the energy used in that, and we got a value of this, and the details are there in the paper. From scrap, again you can see that there's a reasonable range, and of course the point to note is that the energy used from scrap is significantly lower than that in this case. And similarly, in the case of aluminum, in our case, the aluminum from ore, the energy, embodied energy is actually lower than the international number. That's because of the current, the basis based on our production and our efficiency of our manufacturing. And then this is from the scrap. Based on this, now we get for each of the different batteries, lead acid battery, lithium ion, nickel metal hydride, nickel cadmium, sodium sulfur, lithium sulfur, and we get the material per kg of the material, the manufacturing energy, the recycling energy, the transportation, and then we get the megajoules per watt hour of the battery capacity. And you can see that there's quite a bit of variation in this. Lead acid, of course, seems to be low in terms of the embodied energy, and that is why lead acid is actually quite popular. Its initial costs are also low, life is less, and it have environmental impacts. So the PV panel numbers, if you see, this is the breakup of the starting from quartz, the metallurgical grade silicon production, and then the solar grade silicon, and then and so on, and then coming into the glass and copper, the frame, aluminum, and you can see for each of these components there are different energy inputs which have been calculated, and you can find more details in this paper. This gives us finally the kind of values. So if we look at the different batteries, when we talk about the batteries, you can see the difference in the cycle life. You see lithium ion has much higher cycle life than the lead acid, and then the other ones something in between, and the life and the efficiency, specific energy, the energy rating, and of course depending on the battery efficiency for a particular requirement, the ratings on the same functional unit, same basis, we will have different ratings, and that's used for calculation. And so essentially this is the kind of, so you can see, as we said, the storage capacity, lead acid is 150, lithium ion is a little lower, 137, little less than 140, and then these others are in that kind of range. And you can see this is the basis by which we have done these calculations. Based on this, then we have calculated all the different components, the recycled energy, the embodied energy, the cost of manufacture, and per unit mass of battery. If you see, this is how it gets calculated. You can see the energy densities, and you can see lithium ion having the higher energy density, sodium sulfur even higher energy density, and then this comes out in this form. So finally, when you look at the numbers, this is how the numbers look. The interesting thing to see is that per kilowatt of output, which we talked of, this is like the CED, which we talked of, the cumulative energy demand. What is the energy input per kilowatt hour of output? This is not including the solar insolation which is there. This is only the amount that we are using to make this, and you can see that the lead, the lithium ion turns out to be the lowest energy, embodied energy, and so, also you will find that the battery adds a significant amount of embodied energy to the total, and based on that, what happens is that we can calculate you can see that in some cases the battery nickel cadmium, the embodied energy is very high, and of course this also takes into consideration the difference in the lives, because this is the final cumulative energy demand, and it gives us an idea of a comparative idea of this. It shows that sodium sulfur lithium ion seems to be the options which can result in cost effective options. Today they are costly, but they are, from an energy viewpoint, they are actually seem to be promising. And we can also use this as a basis for seeing if we want to change the process of manufacture. Can we change the process so that the energy input actually decreases and it becomes more viable? So you can look at these more details in the paper, and when we compare this, now convert it into the NER, and of course the higher NER is better. You can see that the lithium ion NER is of the order of about 7, which includes the PV plus battery plus the power electronics, and seems to be better than the NER of even the lead acid, and but lead acid seems to be better than most of the others. And you can see the payback period is of the order of about a little more than 2 years for lead acid and lithium ion. And this gives you an idea of, and you can compare these results with the numbers that we saw earlier from NREL and global numbers. You see there are some variants, and that depends on the Indian context as well as the scale at which we make these calculations. We've also calculated then the embodied carbon of the batteries, and then this can be used to look at the CO2 options.